I can start.
Yes, you can.
Great. Okay. Let me go back. So from now on, I will take, just positive mass, and remember our operator dm, which have this form, the matrix, the Dirac matrices, and the Pauli matrices. And you see when you write it when you write the full matrix, so you have in the diagonal the mass, where here we are changing sign, and you have partial derivative in the anti-diagonal. Okay, as I said before, this operator is self-adjoint to one on the domain H1, and the spectrum is essential and is given by this union, these two intervals. Those are the important formula. So when you take Z, just a complex number, and you take this product, then you will get Laplacian plus m squared minus z squared. Okay, well, minus Laplacian here, sorry. And since we know what is the fundamental solution of these guys, it's easy to compute. In fact, the fundamental solution of this Laplacian is just this exponential over cut p of modulus of x. And so if you apply dm plus z, then you will get that phi z fundamental solution of Dirac operator is given by this formula. And then I would like, to pick your attention on the following fact. So in fact, you can write this kernel as follow, avoiding, singularities. So here in the first term, we have just, something which behaves like 1 over modulus of x when x goes to 0. Similarly, for the second term, since we have here x, and here also we will get x here, and in the end, we'll have something which is strongly singular. Okay, so here, this last term behaves like 1 over x squared. Okay, so let's go back, to the main subject of this talk. Again, here I'm taking omega plus to be a bounded domain in R3. I'm denoting by sigma the boundary and omega minus the exterior domain. So what we'd like to do is to study in the perturbed Dirac operator H2, which is given by dm plus A2 delta of sigma. Okay, so delta here is the Dirac distribution supported on sigma, and A2 will be a bounded operator in L2 of sigma to L2 of sigma, which we ask to be self-adjoint and invertible. Okay, so we allow A2 to be, dependent on parameter. So some example, we have the first one, which is just a combination of electrostatic, here the epsilon, and mu beta, which is the Lorentz scalar potential. Another interesting model, which is given by this one, is called the anomalous magnetic potential. And I recall here, n is the outward unit normal to omega plus. And finally, something which is more mathematical, and I don't know how to give the meaning, physical meaning, but we can take A to be, just a Cauchy operator. I'm going to define this in a couple of minutes. So in the rest of the talk, I'm not, present all the catalog, but I will just present some result about the first potential, okay, which is, very well, studied in the literature. So let me just be, at least, say some works. So in fact, in this situation, so what I'm denoting by H epsilon mu is just this operator, the free Dirac operator, plus this potential, okay? So in fact, there is two situations. The first one is when this difference, so epsilon square minus mu square is different from 4. then in fact, in this situation, we can define a self-adjoint operator which give, I mean, a rigorous definition of this partial differential operator. And first people who studied this are Dietrich, Exner, and Shiba. In fact, they introduced this kind of relativistic shell interaction, and also Shabani and Vayabendi. And both paper deals with spherical domain. So omega here is just a ball. And it took, I mean, long time to deal with, say, more general domain. And the first paper who did where this was did in is by Arizabalaga, Albermas, and Wisbiga in this 3 paper, where here, in fact, I mean, they opened the door somehow, and I mean, this topic becomes, I mean, more interesting because of the difficulty and challenge that are behind. And also people from Graz and Prague and everywhere here in Europe, for example, Jussi Bernd, Pavel Exner, Holzmann, and Lothar Schick, where, I mean, those are people which are more involved in techniques of symmetric operators. Okay, so they are very specialist on this topic. And there is a second case, which we call critical, and we will see why this is the case. In fact, in this situation, if you assume that the domain omega is C2 smooth, that is, I mean, locally is given by a function which is C2 smooth, then the operator turns to be essentially self-adjoint. And the domain of the closure, recall that essentially self-adjoint means that the closure is equal to is self-adjoint and is equal to the adjoint operator, of course. So in this situation, in fact, the domain is not included in any Sobolev spaces, HS with S strictly bigger than 0. So you have just the L2 regularity, and that's it. And this was shown by Thomas Ormier Bonafo and Wisbiga, and also by Jussi Bernd and Marcus Holzmann. These 2 papers deals with when the parameter mu is equal to 0. That is just the purely electrostatic case. And there is also a paper by Bernd, Holzmann, Ormier Bonafo, and Ponkrashkin, where they studied, I mean, the analogous of H epsilon mu in 2 dimensions, where, I mean, instead of taking surface sigma, they took a C infinity curve. Okay, we can define, I mean, in the same way this operator. So say, I mean, there is a lot of people who contribute on this domain. I would say I would suggest those references if someone would like, I mean, to get in touch or to get in this business. Okay, so a couple of say problems that when I started, I mean, this subject, this was, I mean, works that I did in my PhD thesis. So somehow, when the domain omega is bounded and C2 smooth, situation, as I said, I mean, was clear. I mean, we know several property of that operator. And so my goal at that moment was, I mean, to consider, I mean, more general situation, not just, I mean, perturbation of electrostatic and Lorentz type. I did with many other interaction. And also I considered, I mean, no smooth domain and non-compact surfaces. So that was, I mean, somehow what I did before. And also there is something which happens in the critical case. So in fact, if you assume that omega is smooth, and say we can prove that, I mean, the operator is self-adjoint. So somehow we have this following problem, which says, is it true that the essential spectrum in this situation is given by this union? In fact, I was motivated by the following paper by Bernd, Holzmann, Ormier Bonafo, and Ponkrashkin, where, in fact, as I said before, I mean, they studied, I mean, two-dimensional analog, and the answer to this question in this situation was yes, this is the case. Okay, so I have been motivated also by this question. So I studied this question for locally compact hypersurfaces. I will give, I mean, the result later on, and hopefully, if I have time, I will give, I mean, the answer in 3 dimensions when the domain omega is smooth. And I mean, it's a very interesting result. And as I said, the other goal is somehow in the critical case, we need regularity. So the question in the non-smooth case must be addressed for non-critical interaction. Sorry, here this should be different from 4. Okay, and we ask him in a question about self-adjointness. At least in Lipschitz, in the Lipschitz case, I mean, Lipschitz are very nice domains. And in the case where we can say something about self-adjointness, so when, what can we say about, I mean, the spectrum in this situation? And also something very important is to see how, say, the spectral property of this operator, or at least its Sobolev regularity, depend on the smoothness of the surface. So maybe I cannot, I mean, discuss this last part. If I have time, I will do it, of course. So first, I will give you the first definition of this Hamiltonian, okay? So I recall here that the definition. In fact, there is 2 ways of defining this operator. The first one, which is, I mean, somehow the von Neumann technique. So in fact, you try to define this operator in small domain, okay, where, I mean, this operator is well defined, and you try to make it bigger, bigger, and bigger. And there is another approach that I would like to start with now, is to define this operator in a large domain, okay, and then try to make it smaller somehow. I mean, we do a reverse technique. So let's start with this. So the goal, so we are looking for, say, a domain in L2 of R3, such that this guys would be a self-adjoint operator. Okay, so assume that we are given phi in the domain, then the delta distribution should be equal to something which lives on the boundary. So in L2 of sigma. And when we apply this operator on phi, then it should be in L2. Okay. So from these 2 points, we see that in the sense of distribution, the free Dirac operator, when we apply to function in the domain, must be given by this. So here we have a regular part, which is in L2, and we have singular part, which lives on the surface. So, and therefore, the domain of our operator should be a subspace of this set, okay? So here, since we have this, that means that phi is the convolution by the kernel of the free Dirac operator with this function, okay? And in fact, since the convolution of phi with f, which is in L2, gives, in fact, the resolvent of the free Dirac operator, that takes value from L2 to H1, then in fact we get the convolution of phi with f is an element in H1, okay? And the convolution of phi with g, I'm denoted by capital phi of g. So and capital phi of g here, sorry, here I use this notation. So phi here is just phi 0. So in the kernel of the free Dirac operator, we take z is equal to 0. And the mapping phi here takes value from L2 of sigma. So it takes something which lives on the boundary and gives you something which lives in the whole space, okay? And is defined by this integral. So we integrate along the boundary and we take somehow the convolution with this kernel. So now, in order to ensure this inclusion and the fact that H epsilon phi should be in L2, one need, I mean, 2 things. So the first thing is that this mapping should be bounded from L2 of sigma to L2 of R3. And also, say the trace from the interior and the exterior of this mapping, okay, should exist and belong to L2 of sigma. And this is to give meaning for the delta distribution, okay? And also we need that, I mean, the restriction of U must be in L2. So if you have these two things, then one can compute in the sense of distribution H epsilon mu applied to phi. So here we'll have dm of u. This guy is in L2, so it's okay. We can forget about it. And when I apply dm to the mapping phi of g, this is the fundamental solution. So it gives us g, and it's supported on sigma. And when we apply the Dirac distribution, here we just take, I mean, the mean value. And since u is in H1, when you take the mean value, it just gives you, I mean, the restriction of u on the boundary. Here, we don't have such things because of the singularity of the kernel. Remember what I said before. When we decompose this fundamental solution, we have last term, which is too singular. Okay, it behaves like 1 over x squared. And somehow there, one need to have, I mean, a jump, okay? And in fact, this is the case. So in the Lipschitz case, for example, we can show that, in fact, in a sense that I will explain in a moment, if you take, for example, when you approach the value of this mapping, okay, then you have this jump formula. So here alpha n here is the normal plus z here, and this is the Cauchy operator. Here I'm putting the dependence on z. So the Cauchy operator is defined as the principal value, okay? So it takes value from the surface and gives you value in, and maps you to something in the surface, okay? With this, if we replace, if we take into account this formula in the last slide here, then you end up with this, okay? So one must have this condition, which we call a transmission condition. So here we are relating, I mean, say the regular part with the singular part, okay? And I'm denoting by lambda of lambda plus this operator, okay? And then with this, we have our first definition. Here, of course, I'm taking epsilon mu in R3. They are both different from 0. And we, under this condition, otherwise this is not well defined. Then in this way, we can define this Dirac operator on the following domain. So here we add this condition, the condition that we found here, okay? And thus our operator acts like this free Dirac operator on the regular part. And this is for all function writing like u plus capital phi of g. And that's mean that here, the Dirac distribution here applied to phi is just the mean value, okay? Let's just go back to this question of approaching from the interior or the exterior. So let us fix a point x on the surface, A positive. Then we denote by the non-tangential approach region of opening A following set, okay? So imagine that you have a point on the boundary, then you dress that, I mean, you draw a cone like this, and you take limits from inside that cone. So if you have a function u that takes value from omega plus or omega minus, then non-tangential limit is this limit. So you take all the limits, okay, from that cone, okay? That's what we call non-tangential limit. Then, in fact, it was shown by Aridabalaga, Mas, and Bega that in the Lipschitz case, in fact, our operators CZ, phi are well defined, and in particular, phi is bounded from L2 to L2 of R3, and the Cauchy operator is bounded from L2 of sigma into itself. And moreover, we have the following property. So the first one is the Plimel-Stochastic jump formula. This is like, I mean, imagine why you are in 2 dimensions, okay, and you have the Cauchy transform, and then when you take limit, say from inside and outside of a domain of curve, sorry, then what you get here is the Hilbert transform, and here, I mean, you don't have you have 1 over 2 plus minus something like that. And also we have this very nice algebraic identity. And lastly, the adjoint of the Cauchy operator is equal to C of Z bar. That means that when Z is in the gap minus M and M, then this is a self-adjoint operator. Okay, so let me give you that, I mean, 2 idea how to prove this. So in fact, the first formula to prove this one, remember the singular part of the kernel. This is, I mean, the guy that plays an important role in study of Dirac operators with shell interaction. So in fact, when you take, I mean, non-tangential limit from inside or outside, then this gives you this, and this is the raised transform, okay? And if you plug this, and then it is easy, I mean, to show this formula, okay? And the second formula is based on following reproduction formula. Somehow here, instead of taking F, you take the map phi defined on omega, okay, and you use this jump formula, and with this you can immediately get the second formula. And the last one is just, I mean, the property of the kernel, I mean, the property of Dirac matrices. I mean, those 3 properties are very, very important. Okay, so now let me give you, I mean, second definition. And for this, I would like, I mean, to recall some result. So assume that omega is C1 gamma domain, that's a Holder domains. And here gamma is between 0 and 1. And define this Dirac Sobolev space, which is a Hilbert space and so on. And in fact, in this situation, the map phi of Z is bounded from HS of sigma to HS plus 1/2, okay? And this is for all S between 0 and 1/2. And it holds that the non-tangential limit of phi is equal to the trace of phi. Okay, so the trace in the sense of Sobolev space. Okay, and we have again the same formula, and in particular, sorry, here this should be gamma. When omega is C1 gamma with gamma strictly bigger than 1/2, then this mapping takes H1/2 to H1. Okay, and in particular, we get also that the Cauchy operator is bounded from H1/2 to H1/2. And in this situation, again, under this condition, the trace operator has a continuous extension to a bounded operator from this Dirac Sobolev space to H minus 1/2. Okay, and secondly, the mapping phi of Z extend continually from H minus 1/2 to this Dirac Sobolev space. Okay, and we still here denote the continuous extension by phi of Z. And finally, the operator CZ is a continuous extension, has a continuous extension from H minus 1/2 into itself. I mean, this is immediately a consequence of this fact, and by duality, I mean, you get this result. So all those results have been known, I mean, for C2 smooth domain, was proved by Thomas Ormier and Luis Biga, Jussi Bernd, and Marcus Holzman. And here, generalization for this kind of domain is not, I mean, so difficult. So here we have this property. Now, to give the second definition, let me assume that the domain, say, is C2 smooth. Then we can define as follows. So remember that in the first definition, I said that G is in L2. So here I'm taking G in H1/2. Okay, so because of the property of phi in this situation, here the domain is in H1. Okay, so now if I take phi in that domain and I'm denoting by phi plus minus the restriction of phi on omega plus or minus, then we have the restriction is in H1 half. And now if I define the Dirac distribution as follows, then one can compute, I mean, very easily in the sense of distribution and get that H epsilon mu applied to phi is just dm of phi plus a direct sum with dm of phi minus plus this term, okay, which lives in the boundary. Okay, and now if we use this the jump formula that I gave before, then we see that this term must vanish. Okay, it is equal to 0. Okay, and this condition holds in H1 half. And since this guy is in L2, so if we take any function in H1 of omega plus, H1 of omega minus, that satisfying this condition, this transmission condition, okay, then we will get H of phi in L2. Okay, so that's mean that we can define our Dirac operator in this following in following sense. So we take just phi in this space such that this transmission condition, okay, this condition relating the trace from the exterior and the interior, it should hold in H1 half. Then our operator is well defined. In fact, both definitions are equivalent. Okay, so there is two definition, and in most of the works, I mean, people are using this definition somehow. Okay, so now we know how to define our operator. So let's see what we can say about, I mean, the spectral property. So from now, unless, I mean, stated otherwise, I'm going to take omega plus city smooth domain. So I'm recalling here the definition of the domain. Then we can see easily that, I mean, C infinity of compact support function outside of sigma are in fact dense in the domain, which is included in L2, and then the domain is dense in L2. So here, remember, this means that our operator is densely defined. So here, L2 is our Hilbert space. Now, the fact that our operator is symmetric can be checked very easily. So if you compute the difference, then you will get this relation. And since our lambda plus, so remember that lambda plus contains the Cauchy operator with matrix which are, I mean, self-adjoint. In fact, this operator is self-adjoint, so we can take it to the other side and we get 0. Okay, so we have an operator which is densely defined and symmetric, and that's mean it is closable. Okay, and moreover, one can check that the domain of the adjoint is given by this. So remark that what's happening here, that, I mean, singular part lose regularity. So here we are in H minus 1 half. Okay. So here, the lambda tilde here, I'm denoting the continuous extension in H minus 1 half of lambda. Okay, so remember that, I mean, the Cauchy operator admit a continuous extension in H minus 1 half. Now we can give, I mean, the first result. So which is the following. So if we assume that this difference is different from 4, then in fact our operator is self-adjoint and the domain is given by this. So here we gain regularity. So remember, we have been in L2 and now we are in H1 half. And this domain is included in H1 because of the property of phi. Now in the critical case, in fact, the operator is essentially self-adjoint. That means that closure is self-adjoint and the domain is given by this one. And here we lose the regularity. So have been in L2, now we are in H minus 1 half. Okay, so how to prove this result? So let me just define the conjugate operator of lambda plus that I'm denoting here lambda minus. So I'm changing just the sign and recall the definition of the Dirac Sobolev spaces. Then using the property of the mapping phi and the fact that the domain of the adjoint. So we have two things. Okay, let me just go until the end. We have the case where epsilon square minus mu square is different from 0, where we need to show that, I mean, we are self-adjoint. That means that the domain of the adjoint, that this domain is including the domain of our operator. And to do this, we compute the product of lambda plus with lambda minus, and we use this identity, and we get the following. So we get this number, which in the critical case vanish, and in the non-critical case does not vanish, and we have this operator. So since lambda plus, when we take g in h minus 1/2, and if we assume that lambda plus tilde is in h 1/2, then this guys is applied to g will be in h 1/2. Okay, and now if we can prove that these operators takes value from h minus 1/2 to h 1/2, then we are down. And in fact, this is the case. These anti-commutators are in fact extend in fact to a bounded operator from h minus 1/2 to h 1/2. So doing this, so in non-critical case, we take these two terms in the other side and they are in h 1/2, and we end up just with a constant type multiple of g, which is in h 1/2. And that means that in fact, the singular part in the domain of the adjoint in the non-critical case is in fact in h1. And that's why we get, we gain the regularity. Now, in the critical case, this factor disappear, okay? So you cannot, in fact, the only thing that you get is that this product extend to a bounded operator from h minus 1/2 to h 1/2. And in this situation, this helps us to prove the inclusion of the domain of the adjoint to the domain of the closure. And that's the end of the proof. Now, let me give you some spectral property in the non-critical case. So here I'm denoting by lambda z. I'm putting here the z in the Cauchy operator. So if we assume that we are not critical, then we have that the essential spectrum of h epsilon mu is equal to the essential spectrum of free Dirac operator. Inside the gap, we have just a finite number of discrete value, okay? And we have this kind of Birman-Schwinger principle. So this says that the value z is in the discrete spectrum if and only if 0 is in the spectrum of lambda z, okay? And moreover, we have this last, I mean, important, I mean, the last, I mean, property makes a difference between Schrodinger operator with delta interaction. So here in the case of relativistic shell interaction, in fact, if we assume that the difference, sorry, here, one of them should be plus. So if we suppose that epsilon minus u is strictly bigger than a certain m, okay, or smaller, or epsilon plus mu is smaller than m, then in fact the discrete spectrum is 0. Okay, so we don't have a discrete spectrum in the gap. So typically for Schrodinger operator, for example, you have, I mean, lower bound. Okay, so you have a threshold. From this threshold, I mean, you can create, I mean, eigenvalues. So in the relativistic, I mean, case, this is not, I mean, the situation. So the first here property flows from this Crane type or Rosenthal formula and the Weyl theorem. So here both are self-adjoint operator, okay? So in fact, here when you take the difference, and because of the property of this operator, which is compact in L2, so the difference is compact. And we have Weyl theorem, which says that in fact, the essential spectrum of these guys is equal to the essential spectrum of these guys. And that's why we have a first property. And the second one is a consequence of the Sobolev regularity that we have. Okay, so last one, I mean, we need to work. So the last last statement is just consequence of this. And this one, you prove it by hand. Now, let me just give a definition about quantum confinement. So when you take an essentially self-adjoint operator H with domain in L2, then we say that this Hamiltonian generate confinement, or equivalently that sigma is impenetrable if for any datum, if when you take the psi in the domain of the closure, which is supported in omega plus or omega minus, then the unique solution psi in C1 of this space that solve this Cauchy problem remain for all time supported in omega plus or in omega minus. That's mean, in fact, for when t is equal to 0, if your particle is inside omega or outside, then this particle cannot, cross the surface and join the other region. Okay, so in this situation, the operator, the closure of your operator, decouples into self-adjoint in the orthogonal sum of two self-adjoint operator, one which acts in interior and the other one which acts in the exterior. Okay, and this means that when you write, the solution of this using this propagator, okay, so if your function is supported in omega plus, then this term should vanish, okay, and vice versa. And in fact, in our situation, the operator, the Dirac operator, in fact, induce confinement if and only if we are under this condition. Okay, so here we are not critical. All right. So let's now pass to say the critical case where things are more funny. So we have this first result by Arizabalaga, Mas, and Biga. They studied, in fact, the case where mu is equal to 0. So this is just the purely electrostatic case. In the case where the surface is hyperplane. So, and they showed that 0 is an eigenvalue of this operator with infinite multiplicity. And in fact, we have this inclusion. Okay. And in another, in the paper by Bernd and Hosman, they showed that, again, for the purely electrostatic case, if you suppose that the domain omega plus is bounded and the boundary contains a flat part, of course, of measure strictly bigger than 0, then you still have this inclusion. Okay. Now, lastly, I would like to recall the result by Bernd, Holzmann, Omier, Bonafont, and Ponkrashkin in 2 dimensions. So here we take a curve, C infinity curve, and we suppose that we are in the critical case. As I said before, they showed that we have this point which belongs to the essential spectrum. Okay, and notice that because of this condition, this point, when you move in epsilon and sigma, this point, this point can take any value in the gap. Okay, and does not touch m or minus m, of course. So the question, is it true that this result for general domain in R3? Okay, so the first thing that I studied in one of my papers is the case of locally deformed half space. So here we take a surface sigma, which is parameterized by this function, which is C2 smooth and compactly supported. So you have just local deformation of hyperplane. So outside the compact set, you are flat. You have hyperplane. In fact, in this situation, the question is yes. The answer is yes. Sorry. So we still have this this point in the essential spectrum. Okay, and it's more harder to prove this result because the surface is infinite. I forgot to say that. In fact, in this situation, we still are essentially self-adjoint without any problem. And the proof is based on the Birman-Schwinger principle and also Crane type reasonable formula for this critical case. And we need to use localization and compactness argument. So but in the end, I mean, we get, I mean, the same result, and we are not, I mean, happy. Now, I still have, I mean, time.
You have 5 minutes.
Okay, so I'm down, yeah. So now, let us assume that our domain omega plus is C infinity smooth, and denoted by kappa 1 and kappa 2 as principal curvature at x. So now define tau to be, I mean, the maximum of the difference, okay? And let E sub sigma epsilon mu be, I mean, the intersection of these two intervals, okay? Then this is a new result. I mean, we have proved this, I mean, a couple of weeks ago with Konstantin Ponkrashkin. He's my supervisor, postdoc supervisor. In fact, we showed that in 3 dimensions, when omega plus is C infinity smooth, and if we are in the critical case, then the essential spectrum is characterized by this. So in fact, we have this interval, okay? Couple of remarks. First, note that, I mean, this interval, okay, reduced to this point. Remember that, I mean, in the preceding result, we have just minus mu over epsilon in the gap. So in fact, this interval reduced to this point if and only if sigma is the sphere. Because when you have, I mean, if kappa 1 is equal to kappa 2, then this means that sigma is the sphere, okay? Or the hyperplane, of course. So here I'm supposing that I'm dealing just with bounded domain, okay? And now I have a problem for geometers, okay? So open problem, say, for which, I mean, if we suppose, for example, that we are fixing the volume, or we are fixing, I mean, the measure of the surface, or we fix, I mean, the Gauss curvature, or the mean curvature, or the genius of the surface. Of course, I mean, the genius should be, I mean, bigger or equal to 2. Otherwise, I mean, we are down. So the question is that, what is the surface that minimize this maximum along all, I mean, the surface or domain with fixed volume? And so one need, I mean, to take one of this constraint. Honestly, I don't know. I don't know, and I would be very happy if some of you, I mean, have an idea how, and if you know, I mean, some result about of this kind, of course. So that's where I should to stop, I think, because I think it's okay. And let's pass, I mean, all those things. And thank you for your attention.
Okay, thank you very much, Badreddine, for this nice talk. So